Hi, and welcome to Erik's Electronics Workbench. In this video, we'll take a closer look at a DC high voltage power supply I just picked up. So let's get started. Here's a high voltage DC power supply, and I'm not familiar with this particular model other than its output rating. It's a 0 to 1000 volt DC, 0 to 30 milliamps. And it's made by BERTAN Associates. I don't have any other equipment manufactured by them, so I'm not particularly familiar with that manufacturer either. You can see on the front, basic power on-off switch, polarity indicator LEDs, most likely the output voltage polarity. It looks like you can switch that. The meter if you're going to read voltage or current, and the output voltage adjustment. It looks like a multi-turn, maybe a 10-turn potentiometer. As you rotate that, the numbers count by. I don't know if those numbers are associated with a voltage reading. You know, if this was turned up to say, 70 or so, would that be 70 volts? I don't know. We'll find that out. I don't know if the power supply works, so we're going to investigate, take a closer look. Again, the BERTAN, it's model 205A-01R. So take a look at the back side. And on the back we have, of course, the line cord, just a standard 120 volt input, marked 115. Looks like it's selectable, maybe 230, you could select that. Fuse. They've got a remote programming. Looks like we've got the local, which would be the front panel, some type of an analog and a digital input. I have no idea what's involved with those. Again, I don't know anything about this other than what it's really rated for the output. So I was not planning to be using this for any kind of remote programming anyway, so likely won't even be investigating those. I'm just going to be using the front panel voltage control. Looks like some power transistors, the 2N6578 made by Motorola. And here's the positive negative polarity switch. And high voltage output connector. Now I don't have this mating connector. I'm going to have to find exactly what that is. It looks like almost a triaxial design. It's got the output threads, and it looks like a BNC connector on the inside, the diameter, but it's certainly, you wouldn't be able to fit a BNC on there. And it looks like an N connector, but it's too big. It looks like an N connector, but it's just a little bit bigger than N connector. So I'm not sure on that, if I can find that or what we can do on that. But for now, we'll leave that alone. We can certainly probe into that for any readings and get that figured out. So we'll leave that as is for now. One of the first things I like to do on power supply before even powering it up, of course we'll take the top off and look around, but take a look at the fuse. You never know, something like this, what's been done, if it has the right fuse. So let's go ahead and take a look at that. And 250 volt, 1 amp. And if we look on here, yep, 1 amp. So it's the right fuse. So just good to check that. Again, everything about this is unknown, so I want to go through and make sure, that somebody didn't put a 10 amp fuse in by mistake or something like that. Or if the fuse was blown, that would be an indication that there was a problem. So get the top cover taken off, and let's have a look inside, see what is going on with this power supply. Hopefully it looks good. We'll find out. Okay, I have all the screws removed from the top cover. So the top cover will come off, and let's see what we have in here. So, pretty clean layout. Power transformer over here. Looks like a big filter capacitor. Of course, the meter looks pretty clean inside. Oh, something's going on over here. This doesn't look original. If you can see in here, let me zoom in. Oh, here, this does not look original. Everything looks really clean in here. That resistor here, I don't know what's going on. That looks like a hose clamp like you'd have on a radiator hose or something. I don't know exactly. That does not look original. So we'll see what that's all about. So we've got a couple circuit boards here. Real clean wiring on they've got the wiring that's all loomed in here, routed around. That looks really good. They've got a resistor over here, but It's kind of floating along on those leads. It looks original though. Some point-to-point wiring in the back. These transistors, going to bring this over here a little bit. Those are where the power transistors are mounted on that heatsink on the back. And you can see there's a group of resistors in here. It looks like emitter resistors. Looks like they're paralleling them together. Base resistor. It's probably the collector. Looks like it hooks in up here on each one, the case. So, but looks like some point-to-point wiring. Don't know exactly when this was manufactured. It's kind of an old school, old style look with the point-to-point wiring, but then the circuit boards, of course, you know, integrated circuits and so on there. So surprised they didn't put those on some circuit board, but it works. You know, there's nothing wrong with that. Just a little bit of a different way to do that. Real clean though. Wafer switch over here for that. Looks like the for the polarity. Now these are high voltage leads over here. Now, what's going on here? We've got, so this resistor right here. Let me back out a little bit here. Whatever this resistor is that someone added in here, it's kind of mounted in here, and it's got this hose clamp around it, and they've got some rubber, and then looks like they've got some wire. That is not soldered very well there at all. This terminal, that barely, I don't know what's going on there. That doesn't look like a good solder at all. They've got this. It looks like they stripped the insulation back on this high voltage lead and tied in right here with a little bit of solder and brought that, and a ground wire here, and they did the same thing. That definitely needs to be cleaned up. That's, in fact, this that's the 1,000 volt. You know, if this is set to the maximum, you'd have 1,000 volts. You'd have 1,000 volts on this wire, and they, you know, the cover is right across here, and they've just left that open. That's not looking too good. So we're gonna have to clean that up. Now it looks like everything here is low voltage on the rest of the unit. Of course, you know, these control circuit boards and then, you know, probably the driver for the transistors and so on, but all the high voltage is in this module over here. So I have no idea what's in this module, but my guess is with these transistors, they've probably got maybe an oscillator and then the high voltage, you know, the oscillator, these drive the oscillator, and it's all encapsulated in here. This is kind of a soft, there's little dings and dents here, maybe just in manufacturing, but it has like a soft feel to it, like a silicone, you know, kind of a soft molded feel. It looks like a block that they've completely encapsulated all the high voltage electronics. And these high voltage wires come out. It goes to the back side of the switch. The front side of the switch looks like it's low voltage, and then this is the main high voltage lead coming out to that connector. So those leads, that's all sealed in there. So I'm not going to be able to change that. That lead is not going to reach. If I cut that lead, it's not going to reach. So I'm going to have to do a repair on that and see if we can clean that up a little bit. So everything looks really clean in here. Other than this modification, I'm going to go ahead and power it up. Now, before we do that, let's see what this resistor is rated at. Looks like they've just got this like a dummy load, which doesn't make sense. I don't know why you'd have a dummy load across the output or a constant load on the output. It looks like here, so that's a 25,000 ohm resistor, 55 watt, 25,000 ohm. So if we figure with Ohm's law, you could do 25,000 ohms and 200 volts. Let's say we set it to 200 volts on the front panel. It would give us, you'd have 8 milliamps. You'd have 8 milliamps. So there wouldn't be any problem. So if I set this to 200 volts as a test, assuming it works, then we'd have 8 milliamps. This is rated 30 milliamps on the output maximum. So that, you know, we wouldn't damage anything. It looks like this is just across the output. I have no idea why, but might as well use it since it's already in here just as a test to see what the, you know, if it's able to power that and if the current indication on the front matches, you know, what it should be. So we'll give it a test and see what happens. So let's get that plugged in here, and okay, so the cord is plugged in, and let's see what happens here. We've got this set to 0, so there shouldn't be any output at all. Looks like power is on. And if you can see on the front, the positive polarity turned on. So I did notice the rear switch was set to positive, so that makes sense. That would be on. Switch is set to voltage. So let's turn this up here a little bit. Look at that. We got a little bit of voltage coming up here. That's looking really good. That's looking real good. So I'll stop around 200 because we already figured that at 200 volts you would have 8 milliamps. So let's see on the counter. That's pretty cool. The counter, it looks like the counter numbers match the voltage. That's really cool. So over here, if you can see, these numbers look like 200 there, and we've got a 200 indication for voltage. Voltage is across the top scale, 0 to 1000. Flip it over there to current. Spot on. Look at that. 2, 4, 6, 8, and then there would be 10. That looks really good. Interesting. I don't know why they would put that resistor in there, because that's just going to draw a constant load, and I don't see what the purpose of having that resistor in there. Made for an easy test on the power supply, but that needs to go. Those solders didn't look too good. Not good at all, really. And it serves, I see no purpose. There'd be no reason to have that resistor in there. Clearly added. So let's see what we can do to clean those wires up. This ground wire back here, it does not hook to a ground connection on that output connector. It looks like they've got that floating, and I don't know where the other side of that wire goes. If they're floating the ground so that the output is isolated from the chassis or not, I don't know. So let's try something here. Just out of curiosity, let's get an ohm meter. Take a look here at something. Let's make sure we've got no output voltage here. Nope, we're all good on that. From chassis to this ground connection here. Yeah, it's a direct connection. So this output connector, the ground connection, is on an inside sort of a ring. It's not on this threaded output back here, this threaded, this nut, this bulkhead connector. The ground connection is actually on an inside connection, like a triaxial sort of a connector, but that wire actually goes right to chassis ground. I don't know, it looks like it routes around. So if there's enough room on that wire to pull it over, instead of trying to repair this, I'll just move that over to that terminal. But it's already a ground connection, so that doesn't look like a high voltage wire anyways. It's much thinner insulation, so we don't have to worry about anything there with a high voltage, but we'll just move that over. But this splice right here, they didn't cut the wire. It looks like it's just, they cut the insulation away and then sort of spliced in. So we'll clean that up. We'll get this resistor out of there. Okay, I've removed the worm drive hose clamp that looks like it's better suited for a radiator hose or something like that rather than an electronics power supply. So that's out of there, and the resistor is loose, so we'll get that removed as soon as we desolder. And come in here like so. Get this connection here. Now I don't want to destroy this wire, ruin the wire, so I'm going to try and, I don't want to just cut that off because there isn't enough length to reach over. So we're going to, repair this with that heat shrink. Get this taken care of first. Get this wire off of there. Okay, so I have the solder removed from this connection, and it looks like we can get that. Got a little hook bent on the end of that wire. Snip that off. That gets that connection taken care of. And one more. I don't know, this wire that they have, this is a ground wire that goes to the output connector. Routes around the corner, and it looks like it comes over here, something to the module, or almost looks like a ground connection behind it. You can't see it in the camera, but there's looks like a copper plate behind here. I don't know, there's like a ground connection or something that they have going on there. And it looks like the white wire over here solders to that ground, but it has continuity to the chassis, so. Let's see here, we've got, yeah, that looks like there's enough length that can reach over like that, and go right to there, so we don't need to try and save this connection right in here and you know, repair it like this one. So we'll just go ahead and cut that off. Keep as much wire as possible. I cut it after the splice. I'll actually use that section of wire. We'll just remove the solder and this connection that we don't want. They have that twisted around there. There we go. So that resistor is taken care of. It's out of there. All right, the output connector is removed. It's a bulkhead fitting. The nut comes off from the outside. And you can see it says Amphenol on the connector. I'll have to find out what type of connector that is. Again, it looks like an N connector, and then it looks like a BNC inside of it, but none of those connectors actually fit to this connector. It's larger than an N connector, and a BNC does not actually fit inside. So we'll have to see what that connector actually is. You can see this connection, of course, is the main high voltage output in the center, and then there's an outer connection that's the ground, and then you've got the threaded connection out here which actually attaches to the chassis. So in the ground connection here is floating, or if you know it's isolated, but in fact the ground connection does tie to the chassis. So come in here like so and get this out. Okay, I have the output connector cleaned up and ready to go. Reinstall. You can see the two solder connections we made there. They're ready to go. And the next step is to clean up this spot with some heat shrink. And again, the heat shrink I have is 600 volt rated, so I'm going to put 2 layers of heat shrink on this spot where they tapped in for that resistor that we removed. So I have the first piece of heat shrink cut, and we'll go ahead and put the hot air with the heat gun and get that in place. You can see the heat shrink, just a selection of it here. This came from All Electronics Corporation. No, they're not a sponsor. That just happens to be where I purchased this from. Had this for quite a while, but I think they still sell it. And it just has a variety of heat shrink, different sizes. This was the 1/8 inch. It's got 1/8 inch, quarter, 3/32, 1/16, so handy to have different sizes. And the white, you know, blends in nicely, so makes the repair look decent when it's done. We'll get the heat gun on there, and we'll get this first one on here. All right, the second piece of heat shrink is in place over the first one that we just installed. So I'll go ahead and use the heat gun and shrink that one down. Okay, we have our 2 layers of heat shrink tubing installed. So I'm ready to install the output connector, get those wires soldered back in place. But something I just noticed, this output connector is not the original connector for this power supply. So again, here's the connector that we cleaned up. And it's ready to go. And I'm going to install this because I don't have anything else to put back in here for testing. But what I noticed on the back, turn this up like so, you can see this connector, this hole right here, there's evidence of 4 or possibly original holes or something modified. Definitely not original. In fact, you can see where it says J1. That hole comes into that. Not likely that the manufacturer would have had, you know, the markings on the panels so close to a cutout. You can see everything else, you know, the writing is in from the edges, and you know, the ground, the letters aren't underneath the head of the screw, something like that. But that J1 right there tells me that's a little close. This hole was probably enlarged to make this connector fit. So I'm going to install this. I'm not going to put heat shrink tubing on the back side of the connector because likely I'll be taking it back out, and I'm not going to put the power supply into final service until I make a decision on whether this connector stays or not. If I'm going to keep this connector, it's easy to unsolder it and just, you know, add the heat shrink tubing on the wires. If I go with a different style of high voltage connector, it'll just be easy to take out and make that change. So I'm not going to put the heat shrink tubing on the back of this connector, but I will install it because it'll give us a point to probe into that center socket, and we can take some readings and verify that the output, you know, can go. We still haven't turned up to 1,000 volts yet, so I want to make sure that the output can at least go up to the full output. Since this is a bulkhead connector, it installs from the back side of the panel, and it's easier to reach the solder connection by having it out before I actually put the mounting nut. So I'll go ahead and make the solder connection. Okay, the wires are soldered to the output connector, and I left the heat shrink tubing off because this may not be the connector that stays in this power supply. It depends if I can find a mating connector or not. If this is a connector that remains, I'll just take these off and add the heat shrink tubing. If it's an entirely different connector, then these have to come off anyways. But this is perfectly fine to do the initial test. We can just probe into the center socket with the voltmeter, and we'll want to check for a full output voltage of 1,000 volts. We haven't done that yet. We just turned it up to about 200 volts before. So let's check the voltage next and see if this power supply is working. So if you're following along and you're working on one of these power supplies, please know that you do so at your own risk. These power supplies have very high voltage in them and are very dangerous. If you don't know what you're doing or are unsure of the test or a procedure, please use caution, be careful, because again, you do so at your own risk. Okay, I have the power supply turned on and the voltmeter is connected to the output connector. This lead is clipped to the output high voltage lead, and this is on the ground connection. Again, this wire that's the ground on the output does tie to the chassis ground, so I've just clipped it to the chassis right here rather than trying to get into the connector. And the voltmeter is auto ranging, so it says 3 millivolts right now, but it's auto ranging, so it will change the scale you know, as we increase the voltage. So we want to go up to 1,000 volts, or see if the power supply can do that. So I'll start increasing it. Now again, there's no load. We've taken that resistor that was in there out. That was putting a load on the power supply. I have no idea why that was done. So as we start to increase this, and again, there's no load. I'll come up to about 100 volts, and let's see if the meter is accurate, sitting right about there. There's 100 volts, 100.5. Doesn't take much. It's pretty touchy on that potentiometer. Just a little bit of a nudge there. You can get it to change. But okay, so right there, 100 volts. And 102 it says on the counter. So now this counter is a mechanical counter, but that's nice to see that it's tracking so close. So 102. Now the actual reading on the voltmeter on the front, if I can tip this up just a little bit here, you can see there's the 102. And that looks like 100 volts. That looks pretty accurate. Now these meters are not accurate when you're turning the panel or moving them upwards like that. They're accurate when they sit in their normal operating position. So I'll put it back down to read, and if I count the scale, yeah, it's exactly 100 volts. So that does match. So that looks good. So let's increase that. Let's go to 200 volts. Right about there, looks good. 200.4. Again, just a little bit of a touch there. It changes, but that looks good. And yeah, it's spot on. It's exactly 200 on the meter. If I tip that up, it stays pretty accurate there. If we flip that over, yeah, falls to 0. So there's no load. And before, with that resistor installed, this was showing, what did we have? I think it was about 8 milliamps. So, it was up right about in there. So that's good. There's no load. But we'll put a load on it, and we'll verify if that's accurate and take some more readings. But for now, without a load, we'll go back to the voltmeter here, see what we get. Let's go up. Go to 400. Jump up a little bit here. Right there, 400. Yeah, it's just a tiny bit under 400. Just the width of the needle under 400 on the meter. So, not bad. Go to 600. Yep, 600 on the meter. Looks like it's reading just ever so slight under 600 on the meter, but very, very close. So. All the way to 800. Yep, got 800 volts. That looks good. Flip this over here to current. Yep, still down at 0, so that's good. And there we have it. There's the 1,000 volts. There it is. Very cool. So it's able to generate the 1,000 volts. That's the full rated output. And the meter is right on 1,000 full scale deflection all the way over. See there. So that looks very good. That looks really good. Yeah, I'm going to start to turn that down. Yeah, now you can see without that load resistor, it's a lot slower to drop the voltage. That was bleeding off that pretty fast before. If I drop that down, see, it's all the way down to 0, and you can see how it's slowly discharging, which is fine. No problem with that. I just cannot see why that resistor was installed. I mean, that was an unusual, kind of an odd addition to the power supply or modification. Don't know what was going on there, but certainly don't want that in there, and it wasn't done in a safe manner with those bare wires and bare connections. So good to get that taken out, and the power supply definitely seems to be working fine. So now let's check the current, and I'm going to get this repositioned and a different setup so that we can see if the current meter is accurate, and to do so we'll use this multimeter, but I have to make some changes on the test leads, so we'll do that next. Okay, I have the meter set up for a current measurement. You can see the probe has been moved over to the milliamp microamp position, and the current will flow through the meter for this test. The dummy load, or the resistive load on the power supply, is connected into the center pin, or the center socket on the output connector, and I have this stiff wire, attached to it that pokes in and makes a good solid connection into that socket. The actual dummy load is the resistor we just took out of the power supply, that modification that we got rid of. The resistor makes a good test load. It's rated 25 k ohm, 25,000 ohms, 55 watts. So it's a good choice. I probably have a similar resistor in the parts bin, but this resistor was on the bench, so we'll go ahead and use it. And the other side of the resistor connects ultimately to ground. It's on the meter side, so we come out through the high voltage on the connector, through the resistor, on the other side of the resistor, through the meter, and then ultimately to the ground connection. So with Ohm's law, we can figure out what the current will be. If we set for 375 volts and a 25 k ohm resistor, we'll get 15 milliamps at that 375 volts. So 15 milliamps will be the mid-scale, mid-range on this power supply. This power supply is rated 30 milliamps maximum. So with that 375 volts and 15 milliamps, that's a 5.6 watt load on the power supply. And again, resistor is rated 55 watts, so no problem there. And then I want to do a full current draw on the power supply, which is that 30 milliamps. So that will occur using the same resistor at 750 volts. So again, 30 milliamps and a 25 k ohm resistor, Ohm's law, you can figure out easily 750 volts is what that will require to get to that current. And when you have it set for that voltage and current, it'll be a 22.5 watt, 22.5 watt load on the power supply. So the power supply is turned on and ready to start increasing the voltage. So we can see that the current is increasing. So we're going to go to 15 milliamps. So 10. Right about there, 15. I did check the resistance on that meter, on the resistor rather, and it was very close to the 25 k ohm. Okay, 15.01. So, yep, the meter is very close to the 375 volts, and the actual current, yeah, it's exact. It's right in the middle. It's exactly on 15 milliamps. Here's a better view so that you can see the meter on the front panel. You can see it's right in the mid scale, which is 15 milliamps, 30 milliamps maximum, full scale. And if I go back to the voltage, there's the 375 volts. Back to the current. So that looks really good. That's looking really good. And the meter, you can't see in the image now or in the frame, but it's holding right at 14.99, so it looks real stable, looks really good. Okay, now we're going to increase the voltage so that we get a 30 milliamp current draw. So I'll begin increasing the voltage. There we have it. That looks really good there. 30 milliamps. Very close right there. 30 milliamps. You can see on the meter over here, 30 milliamps. There's a 750 volts, I believe was our, yep, 750, and that looks really close. It maybe is a touch high on the voltage, but the milliamps does read. Looks like it's just slightly high on this meter. Maybe reading a bit high if I come down. Let's see, yeah, 29. So, you know, very, very close on the analog meter on the front. So no issues at all. The power supply really seems to be in good condition. It seems to be working correctly. And decrease that. You can see it drops much quicker now with that load on there. This output, you know, it falls much, much quicker. So the one final test or check that I want to make on the power supply is that polarity switch on the back. It's we've been doing all the tests with this indicator, and you move the camera over a little bit here. You know, this indicator has been on positive for the polarity on the output, but I want to make sure that the negative output is working correctly. Now the negative output, if I'm understanding correctly, I believe it should just be switching so that basically the main high voltage lead becomes negative in relation to the chassis. And that's easy to check on the multimeter. We'll just look for a negative voltage indication, so we'll do that test next. Okay, I have the meter set up to measure DC voltage. The positive lead is connected to the high voltage output, and the negative lead is just on chassis ground. Now the rear panel output polarity switch has been changed over to the negative position. So on the front panel, over here we have the negative positive polarity, and it's been on positive. We'll look for the negative LED to turn on. So voltage is set to 0. Voltmeter position, so go ahead and turn that on. And there we have it. So you can see on the digital multimeter, negative indication. I'll bring that up. About 200. Passed it a little bit there, bring that down. About like so. So you can see over here the negative indication, and of course before we didn't have that. So that shows that the polarity has been changed so that the output is now a negative polarity in relation to chassis ground. Now on the front panel, the meter reads, you know, there's no polarity, so the meter is still reading the same on the front panel, but the output polarity is changed because of that switch. So that's a nice feature that the power supply can do that. So the repair and testing on this power supply is complete. The power supply is functioning very well at this time. If you enjoyed this video, please give us a thumbs up. Until next time, goodbye.